All right, so thanks for coming out, coming to our review session here. Minimize that. Let's talk a little bit about just in general what's going on. And then we can get into your questions and talk about, more specific things. So first off, the exam itself. The exam itself is a total of 22 questions, not 18. Not sure how I added that one up. But 22 total questions. 16 of them are multiple choice. The other 6 are short answer. One thing you're not going to need, you can look through this. None of the questions on here are calculation oriented whatsoever. You can pretty much leave your calculation, you can leave your calculator at home for Monday's exam. You're not going to need it. Very similarly to these past 3 quizzes. Haven't needed a calculator for any of those as well. Now, as far as the chapter 6 quiz is concerned, I'm in the middle of grading those. Grades should post either late this evening or early tomorrow. You'll get the quizzes back in lecture. But if you look through here, you can see the split of the content. This is very heavy in chapter 4. And the primary reason it's heavy in chapter 4 is because that Lewis structure drawing business bleeds over into chapter 5 as well, and to a lesser degree, chapter 6. So if you can't draw structures, it's going to be really hard for you to do well on this exam. But you can see in here also, you're going to see questions about lattice energy. You're going to see questions about types of bonding. The majority of what you're going to do, obviously, is going to be about those Lewis structures, drawing them, being able to interpret them. Out of chapter 5, about a quarter of that content is going to be VSEPR related. So can you use those VSEPR tables? Can you interpret a Lewis structure? And from that structure, determine things like shape, bond angle, hybridization. Can you look at a Lewis structure and determine the number of sigma bonds, the number of pi bonds? That's the kind of stuff that you're going to see here. In chapter 6, you just took a quiz over it. Intermolecular forces, knowing the differences between the forces. Being able to use an understanding of those forces to explain, hey, I've got 2 compounds here. This compound has dipoles because it's polar. This one has no polarity, so it just has London forces. What should I expect of that? Which one's going to have a higher viscosity? Which one's going to have a lower boiling point? Those kinds of things. And then just from a general solubility kind of standpoint, what is a solute? What is a solvent? What happens when things dissolve in water? And how do we interpret those phase diagrams? So when you get your quizzes back tomorrow, you will have a chance to kind of go through some of that, see where maybe some of your problem areas are if you haven't identified those yet, and use that to either ask a question or use that to try to focus your studying a little bit this weekend. So all told, there are 87 points on this exam, but your grade will only be measured out of 78. So there are 9 bonus points. It's actually a little bit greater than 10% extra on this. So how you use that is really up to you. You can use that and say, look, I'm running short on time. I don't really know how to do question number 4. It's worth 8 points. I can skip it. And those 8 points, well, those are kind of bonus points anyway. That's one way to interpret it. The other way to interpret it is I go for as much partial credit as I can and know that I've got 9 points of buffer, kind of, where I can make some mistakes and still be okay. So any questions about the construction of the exam itself? Yes. Yes. So just like your homework, the homework is 35 points in smart work, but it's only 32 points in Blackboard. Anything you score above that goes into the book as bonus. So that would help raise your exam average if you did better than the announced total. All right, any other questions, or are we ready to get into some more specific stuff? All right, so I have here the practice test, so we can go through it if we want to. If we've got specific items out of it that we would like to look at, I'll open that up to you first. If there are other concepts that you want to talk about that aren't on here, we can do that as well. So let me open it up to you. Tell me what you want to talk about. Jackie. Sure. So number 1 on the free response. Okay. Here we are shown 2 different forms of the thiocyanate ion. What we're asked to do is pick one that is the favored one and justify our decision. So to do that, how do we tell one resonance structure from another? How do we interpret this one's better than this one is? Okay, close. We need to look at formal charges. Because we can look at this and say, okay, everything's obeying the octet rule. Nothing's going out of bounds in terms of that. Which one's got the better formal charges? That's the one that we're going to favor. And so if we look at this, we can see, okay, remember, formal charge is equal to the number of valence electrons minus the dots minus the bonds. So in both cases, the carbon is exactly the same. I've got 4 valence and no dots and 4 bonds. So I've got no charge on either of the carbons. Carbon's not going to be the thing that sets this in one direction or the other. It's going to be the nitrogen and the sulfur. Now for the nitrogen, 5 valence, 2 dots, 3 bonds. This one also would have 0 charge. For the sulfur, 6 valence, 6 dots, 1 bond. Here's where our -1 charge lies in the ion. On the right side, similar kind of calculation, but we see that basically the 0 and the -1 have just flopped from one side to the other. So now we have to look at this from a perspective of electronegativity. Which atom, the nitrogen or the sulfur, is better suited to hold that -1 charge? And the correct answer is the sulfur. The sulfur is better suited to hold that -1 charge. And so the correct answer we would write is this one on the left is the one that is better suited and the more stable structure. Now, one important thing that does get drawn out here, if we are looking at electronegativity as being the thing that determines what is best suited to carry that extra negative charge, what we're going to find is that the nitrogen actually is more electronegative, and that would lead you to choosing the right-hand answer. And so this is from an old exam. I actually accepted both answers, provided that the reasoning behind them was correct. So it was kind of an all or nothing kind of thing. You had to choose you had to choose an answer and defend it with proper logic and reasoning to get the full credit for the response. Otherwise, you really couldn't get too much partial credit off of it. So the reason we think that the reason that we go with the sulfur in this particular case, this is an analog of the cyanate ion. The cyanate ion has the same structure, only with the oxygen getting the negative charge. We expect something similar out of the sulfur here. We can also think about it in terms of what does sulfur usually kind of carry? It usually carries a -2 charge. Having a -1 charge is not far off from that, whereas nitrogen's -3 is a little bit further away from the -1. So there are some directions that we can kind of go with this. But if we're looking at what is the expected answer, this structure on the left is the one that we would expect. And if we actually went through and did the analysis to look at the structure and look at like bond length and bond strength, we would find a triple bond there. But if you were asked to compare structures, formal charge is the way that you have to go. And so where it really falls is zeros if you can. If I can get a formal charge of all zeros, great. In case of an ion like this, I can't. I'm going to have a -1 somewhere because the whole thing is -1. But if I'm trying to figure out where that -1 goes, I got to look to electronegativity. Electronegativity is the more often than not deciding factor in that. And if you're given a table of the Pauling values, then yes, you can look that way. Otherwise, we always play kind of closest to the pin. Fluorine's the most electronegative element. If you look at the positioning of sulfur versus nitrogen, sulfur appears to be closer to fluorine. That's where we would kind of make that determination. In terms of the Pauling scale, the actual numbers, it's a little bit different. And that's why I had to accept both answers. Any further questions with this first free response? All right. What do we want to look at next? Okay. Okay. Question wants us to identify all of the intermolecular forces that are present between each of the pairs of molecules. And then answer the question, will they dissolve in one another? Well, for answering this second question, what we really need to get into is the principle of like dissolves like. If the two substances have similar kinds of intermolecular forces, meaning all polar or all non-polar, then we know that they will dissolve. If we have a mismatch, then we know that they won't. So when it comes to like dissolves like, don't get too caught up in the kind of nitty gritty of it. And what I mean by that is, oh, well, this one has hydrogen bonding and this one is polar but doesn't have hydrogen bonding. They're not gonna dissolve in each other. Now, they're still both polar. Polarity is all that matters. Oh, this one's ionic and this one's polar. They're still gonna dissolve in one another. Ionic is just polarity to the greatest extreme. What we're really looking for is there a clean mismatch? Is there a polar substance and a non-polar substance? If there is, then we know they won't dissolve. Otherwise, so long as they match at least nominally, they should dissolve in one another. So when it comes to these problems, hopefully we can at the very least recognize what's going on without drawing them out. If I have to draw them out, I have to draw them out. But these molecules should be at least familiar enough to us that maybe we don't have to draw out all of them. But let's just do it for the sake of completeness here. There's ammonia, there's water. We can clearly see in both cases we've got a lack of symmetry in their tetrahedrals. So we know that they are both polar. So in terms of this second question, will they dissolve in one another? Absolutely. They're both polar. Now, as far as the forces are present, we need to look at each one individually. In ammonia, we're going to have London forces, because those are in all things. We're going to have dipoles, because it's polar. Is ammonia going to exhibit hydrogen bonding? Yes. We've got a polar molecule. NH is one of the bonds that we looked for, so we've got hydrogen bonding there as well. In water, I've got the same things. London forces, dipoles, and OH bond there means that we've got hydrogen bonding as well. So as far as the forces are concerned, we're going to put in every single force that they have in common. So London forces are going to be there. Dipole forces are going to be there. Hydrogen bonding is going to be there. And we already answered the second question. Do they dissolve in one another? Yes. Like dissolves like. They're both polar. Alvaro. Yes. That would be fine. All right, let's look at the second example, carbon monoxide, hydrogen sulfide. So in carbon monoxide and hydrogen sulfide, we've got a polar molecule here. We've also got a polar molecule here as well. For carbon monoxide, the lack of symmetry is in the fact that we've got a linear molecule and two different atoms are on it. For the hydrogen sulfide, it's pretty much like water. It's polar because of that asymmetry in the tetrahedral. So for like dissolves like, yeah, they're both polar. So they're going to dissolve in each other. Correct. Correct. So for carbon monoxide, we know we're going to have London forces. We know we're going to have dipoles. Any reason to think we'll have hydrogen bonding here? Right. For the H2S, we're going to have London forces. We're going to have dipoles. We can get hydrogen bonding inside of H2S. No, it's not one of the right kind of bonds. So we know we're going to have London forces. We know we're going to have dipole-dipole. Would we have hydrogen bonding between them? It's kind of a tricky question. Now, as far as the exam goes, I would not hold you to this. If you told me there was hydrogen bonding there, I'd kind of ask you to explain it. But if you could, yeah, you're right. We could get hydrogen bonds to form between the oxygens in carbon monoxide and the hydrogens in H2S. Would they be as strong necessarily? They'd be different. But technically, yeah, it's kind of the same thing that we see in DNA. Where we've got nitrogens that don't have hydrogens on them finding their way to hydrogen bonds in another molecule. So it's a little bit iffy. We can definitely stick to the London forces and dipoles though. So like I said, if you stick with what they have in common, you can't go wrong. Could you make some interesting arguments sometimes? Yeah. All right. Part C, we've got methane and silane, CH4 and SiH4. Is methane polar? Now, I've got a tetrahedral. All four of the bonding positions are all the same, non-polar. What about in the silane? Is there polarity there? No, same reason. Okay. So here's what's interesting. They're both non-polar. So will they dissolve in each other? Yes. Like still dissolves like, even if the two substances are non-polar. But in terms of the forces, since we're dealing with just non-polar substances, we know that the only forces in play are London forces. All right, this is not a question on the page, but it does relate to what you saw in the quiz. Which one of those two would have the greater London forces? Yeah, it's the silicon one. Remember, when we're looking at London forces, we're looking for a property called polarizability. Polarizability has two factors. One of them is the number of electrons, which we can estimate by looking at molar mass. The other one is the shape of the molecule. Now, both of those shapes are identical. They're both tetrahedral. What's the difference? Silicon has 8 more electrons. Those 8 extra electrons, that bigger size overall, means that it's more likely that we're going to get a difference, a differential in electrons, and end up with a positive side and a negative side to make those London forces appear more often. And that's really what polarizability is all about. Can we get those London forces, those temporary dipoles, to occur more often? If I have more electrons, they're going to occur more often. If I have the ability to get those molecules closer to each other, I'm going to get greater attraction due to spacing. All right, let's look at number 4. Number 4, we've got potassium chloride and we've got water. Potassium chloride we need to recognize as an ionic substance. Water, we drew out previously, there it is. With KCl, we are dealing with something that is ionic. With water, we're dealing with something that is polar. Will they dissolve in one another? Absolutely. It's always surprising how many people on the Chapter 6 quiz try to tell me that the ionic compound is not nearly as soluble as something like bromine. If you came to that conclusion today during the quiz, you overthought it. Ionic compounds, they dissolve better than any polar substance because that charge is permanent and large as opposed to permanent and partial. Now, in terms of forces, the primary force that exists between potassium and chloride are ionic bonds themselves. Whereas with water, we know that we've got London forces, we've got dipoles, and we've got hydrogen bonding. Now, what forces draw all of these together? Well, it's exactly everything. London forces are going to hold it together. Dipole forces are going to hold it together. Hydrogen bonding is going to hold it together. And because we have an ion and a polar substance, there's one more force that gets brought in here. Don't talk about it a whole lot, but the ion dipole force is there as well. And so in this scenario, you're going to have everything. Because even though the London forces and the dipole aren't really traditionally there in the sense of potassium chloride, we don't think about them because next to the ionic bond, it's really, really small. But when we start to separate them from each other, we're going to see all of those forces in play. For the last one here, we've got methane and ammonia. We've already drawn these structures. I'm just going to draw them again so we don't have to scroll. He said as he scrolled. We've already established this is nonpolar and this is polar. So will they dissolve in one another? No. And the reason why, like dissolves like, and these are not alike. Every other example that was on this page, they were alike in some kind of way. We either had polarity on both sides, or in the case of letter C, non-polarity on both sides. But if we have polar and non-polar present at the same time, doesn't work out real well. As far as the forces are concerned, in the methane, we know we only have the London force. In the ammonia, we have all of the traditional covalent forces, London, dipole, hydrogen bonding. The only forces in play, however, are the ones that are in common. London dispersion forces. We could make an argument that there are induced dipoles also. Remember, we talked about induced dipoles when a polar substance and a non-polar substance come into close arrangement with each other. The dipole can force a little bit of separation inside of the non-polar object, maybe cause it to bend a little bit. We talked about that in particular with oxygen and how water can bend oxygen slightly enough to get it to dissolve. But that is a marginal kind of thing. Even if we could get some of that induction to take place, the solubility of methane in ammonia is very limited. Very, very limited. It would appear if we had both in liquid form, which for these two chemicals is not as easy to get as it sounds, we'd have a really good chance of it forming layers though. All right, questions with this one? It's kind of a long problem. There's a lot that goes into it though. On this exam, I gave bonus for induced dipole. And if you read the key that gets published at 6 o'clock, you'll see that. So London forces would be completely okay as the answer, but it's one of those, I reward creative thinking if it's also accurate thinking. And obviously that's something that would go beyond the page. So yes, if you were rationally able to come up with that, then yes, I would give you credit for that. Now, that being said, if you were to give me the wrong forces, I don't just look for the correct answers and mark you correct if the correct ones are there. If you give me a mixture of correct and incorrect, I'm going to mark you down for the ones that are incorrect. So don't just blindly guess for things hoping that you'll get bonus points. It could hurt you too. It's more, I would say yes. It's probably more common when we've got hydrogen bonding though, because of the kind of extreme nature of that polarity. Jackie? So we need to look for one of those special bonds. So the difference between water and H2S has to do with the fact that water has an OH bond in it. They're both polar. Hydrogen bonding involves being polar and having one of 3 special bonds: hydrogen, oxygen, hydrogen, nitrogen, or hydrogen, fluorine. So the reason why these exhibit hydrogen bonding and this one didn't is because nitrogen, hydrogen, that's one of the special bonds. Oxygen, hydrogen, that's one of the special bonds. Fluorine, hydrogen, that's one of the special bonds. If I have a polar molecule with that, then I know it's going to exhibit hydrogen bonding as well. Addie? So when we're looking for symmetry, what we need to look for is if I have drawn the molecule, one thing I generally can't have are lone pairs. And if I do, those lone pairs have to be in equal and opposite kind of orientation. So we're talking about trigonal bipyramidal, where we've got 3 lone pairs in that equatorial plane. Square planar, where we've got the 2 lone pairs, one on top and one on the bottom, so they kind of cancel each other out. Otherwise, lone pairs generally indicate asymmetry. If they indicate asymmetry, then that means it's polar. Symmetry really only comes if I have a molecule, no lone pairs, all bonds, and all the bonds are the same. So the methane and the silane here, those both fit the bill because we've got a molecule, 4 bonds around it, all 4 bonds are identical, they're all the hydrogen. That's what makes it symmetrical. So where we can get into trouble is if we don't use those 3-dimensional drawings, we can look at something like H2S or something like water and say, hey, that looks pretty symmetrical. I've got a hydrogen on each side. I've got lone pairs on top and bottom. Maybe it's nonpolar. What we have to remember is that a Lewis structure is not a three-dimensional drawing. We need to get it into three dimensions to accurately portray that. And when we do, we see that the lone pairs are going to be pointing in one direction, the bonding pairs are going to be pointing in a different direction. It's not symmetrical anymore. Now, the probable exception to that is if we start looking at hydrocarbons, organic molecules, CH4, C3H8, C4H10. We have to understand that those carbon-hydrogen chains are nonpolar because the electronegativity between carbon and hydrogen is practically the same, not quite the same, but practically the same. And the structure of that chain is very symmetrical. And so as that carbon chain gets longer and longer and longer, the more nonpolar the molecule is going to get. And I think you saw an example of that. It was either in the skill builder or one of the homework problems where you were asked to evaluate different alcohols based on their solubility. And the rule of thumb was the shorter the carbon chain, the more soluble in water it was going to be. As we added more and more and more carbons to it, it became less and less and less soluble in water because the nonpolar side of the molecule started to become more and more noticeable. All right, any other questions here with this second problem? All right, let's move on to something else then. Go ahead, Sierra. Okay, number 10. Okay. Okay. This is a good question to reference because this is a question that a number of you missed on the quiz today. You're asked to draw basically what happens inside of water when we have a cation or anion dissolving. So what does it look like when we dissolve an ionic compound is really what this is asking. And so we would hope that after 10 minutes of stirring, we shouldn't have too much solid left over. So the idea that we've got a whole bunch of solid here really doesn't make any sense. At the same time, letter F doesn't make any sense either. After all, in letter F, we've got no solid whatsoever in there. It just flat out disappeared. So we can rule out letter B because letter B doesn't really show that the water molecules and the ionic compound are interacting. All it's showing is that we've separated individual pluses and minuses off of the larger plus and minus. So it comes down to D and F. D says that we split off all of the pluses and minuses, but there really isn't any interaction that's taking place between the pluses and the minuses. Letter E says not only have we split them apart, the water molecules are finding their way to those ions and surrounding them. And that's the correct answer. Now, what's important for us to note, and this is where some of you got into trouble on the quiz, is that there is a specific nature to how those water molecules are setting themselves up. If you look closely, I'll see if I can zoom in on this a little bit. Look closely at this plus ion. So this cation, what part of the water molecule is it attracting? Oxygen is red, hydrogen is white. Yeah. It's attracting, so the positive ions are attracting the oxygen side of the molecule. And that should make sense to us, right? Because if we're looking at the polarity of water, this is the negative side, and this is the positive side. So by that very frame of logic, if we look at the negative ions, the chlorides, we should see that the chlorides are attracting the hydrogen side of the water molecule. And indeed they are. You can see it here, you can see it there, you can see it there. The oxygens are clearly being pushed in the opposite direction. The hydrogens are coming in on the other side. And for the exact same kind of line of reasoning. This is the positive side. This is the negative side. Like forces repel, opposite charges attract. And so these were the details a lot of you were missing in that quiz. Some of you just forgot what a cation was or an anion was and did the opposite. And some of you knew that water was involved, but you kind of just put it any which way that you thought it fit. So I saw a number of pictures where there were oxygens and hydrogens both attracted to the same ion. And that just doesn't work. So letter E is your correct answer here. All right. Further questions with this problem? All right, let's take another one. Addie? But number 9, this one? Okay, so D would be an example of an organic molecule. This would indicate a double bond between the carbons. So you're talking about a molecule that looks like this. Yeah, so you're correct. This is the only one that actually exhibits hydrogen bonding. First of all, this one's non-polar. We can see the symmetry of it. And so if you look at all the other ones, this one's non-polar, this one's polar, this one's non-polar, this one's non-polar. There are only 2 polar molecules. Being polar is the first condition of hydrogen bonding. And in letter C, we have none of those special bonds. So A is the only option here. Okay. All right. So 12, 13, and 14 involve this phase diagram. Okay. If you begin at point B and steadily decrease the temperature, so remembering that this axis is temperature, if we are going to decrease it, we need to go this way. What are we going to see? Well, we're going to see a little bit of melting, or I'm sorry, a little bit of condensing, and then a little bit of freezing. So that would be E. We have to remember what each of these phases are. This is the solid, this is the liquid, this is the gas. So if we are going this direction, we're going to see the gas turn into a liquid, that's condensation. Then we're going to see the liquid turn into a solid, that's freezing. Letter C. Letter C represents a spot on this line between the gas phase and the liquid phase. So one correct answer is, we could call that the boiling point. There is an argument that you could make for letter E. Because from letter C, it kind of goes sideways here. You could make an argument that this is actually the critical point. And at the critical point, it's not really vaporization or boiling anymore. We've transitioned into that kind of in-between phase of the supercritical fluid. So again, this is one of those where there were multiple possible answers. And so if a student chose E, I gave them credit for that as well, because that's the critical point also. If you begin at point A, how can you make gaseous ammonia? Okay, so point A is firmly in the solid region. I've got two options there. I could increase the temperature, which means it would go through the liquid first, but we would eventually get it to the gas phase. Or I could decrease the pressure. So increase T or decrease P. Those are the two options. Now you may be saying to yourself, well, why couldn't you do both? And go like this. Well, if that was one of the options, then yeah, you could. So decrease the pressure was one of them. Increase the temperature was one of them. Either A or C would be the correct answer. So this was F. To do both, you'd have to have obviously the option both A and C. But that wasn't one of the options given. All right, further questions. We've got about 15 minutes. Alvaro? What are the colors? The colors? Yeah. The colors are there just to show the differences. They don't actually signify anything. So yellow doesn't signify liquid. It's just, we're using different areas to highlight the differences in phase that there are. I believe the ones that we had that we used in class were like dark blue and light blue and yellow or something like that. You know, that's not a consistency. So look more at the lines. The regions will always be the same. The far left region will always be solid. The far right region will always be gas, and liquid will be somewhere in the middle. Mm-hmm. So ammonia naturally exists in the gas phase. Where we think of it as a liquid is because we dissolve it in water, and that's what becomes the basis of most of our applications of ammonia. Ammonia itself is actually a gas. And so it would exist in the gas phase at room temperature. But we bubble it into water, and then it becomes an ammonia solution, and there it is very stable so long as it is capped. That's okay. Jackie, what was your question? Okay, well, since you asked the same thing, I suppose we can do it. Okay. All right, so you will see a question similar to this on the exam. It's kind of a good way to kind of catch everything out of chapter 5. So let's see, we'll do as many of these as we can, and we'll hit quit in time and go from there. Okay, the nitrite ion. So Lewis structure for nitrite, it's NO2 -1. So I've got 5 plus 12 plus another, it's 18. So there's my Lewis structure for that ion. Now we get into the VSEPR ideas. I've got a steric number of 3 here. So I've got 1 bonding region, 2 bonding regions, and a lone pair. With a steric number of 3, trigonal planar is my domain geometry. With that lone pair there, that's going to make the shape bent. And that's going to change the bond angle from a simple 120 to less than 120. Again, all of that information would be on that sheet that you're allowed to use. Hybridization with a steric number of 3 would be sp2. And I can see that I've got 3 bonds in total. One of them is a pi bond because of this double bond here, which means that the other 2 are sigma. You all should have a copy of it. If the problem asks you to assign individual atom formal charges, then yes. But you could have easily just written this out as follows and been okay. All right. Any other questions from this first one? All right, for the second one, we've got xenon tetrafluoride. 8 for the xenon, 7 for each fluorine, So 36 in total. If I draw out the simple structure, I end up with 32 electrons in total. 8 in each direction times the 4 directions, 32. I'm still short 4. If I find that I'm short electrons, where do they go? They go in the middle. So the xenon's going to carry a couple of extra, which actually works out for the xenon because look at what happens to the formal charge of xenon now. 8 valence electrons minus its 4 bonds minus its 4 dots. It's got a formal charge of 0. Kind of works out for it. But I can see from this, I've got 4 bonding groups and 2 lone pairs. My steric number is 6. So I'm talking about octahedral here. Octahedral with 2 lone pairs would be square, planar. And square planar, since those angles can't, those lone groups cancel out, I'd have just 90-degree angles and 180-degree angles to worry about. For steric number 6, the hybridization is sp3d2. And for bond counting, I've got 4 bonds in total. None of them are double bonds or triple bonds, so I've got no pi, which means I've got 4 sigma. All right, for the next questions about the xenon compound. Jackie? Okay, so if you have a lone pair in the structure and it is not canceled out by other lone pairs. So again, the only ones that this would apply to are square planar and linear. Square planar in octahedral, the linear structure in the trigonal bipyramidal. Those are the only ones that basically cancel each other out. Otherwise, if you've got a lone pair in there, you should have a less than sign. But in this case, those 2 lone pairs are completely opposite each other. So any pushing downward by this one would be matched by an equal push upward by the other one. All right, Si3 negative. 6 for the sulfur, 7 for each iodine, and an additional 1 makes 28. Once I've covered all of the iodine octets, that's 24. I'm 4 short. So they need to go on the center. So you could assign the individual formal charge of -1 on the sulfur, or you could bracket it like I'm showing here. Either way, you've got 3 bonding groups and 2 lone pairs. So that's a steric number of 5. Steric number of 5 means trigonal bipyramidal. Trigonal bipyramidal with 2 lone pairs on it is T-shaped. Bond angles in T-shaped are going to be less than 90 and 180 degrees. Hybridization for steric number 5 is sp3d. And if I look at the structure, I see there are 3 bonds in it. None of them are double or triple bonds, so I've got no pi, but 3 sigma. You have to remember, so if we're looking at the T shape, try to draw this out a little bit heavier. My lone pairs are here. Remember, the 120-degree angles are only in this plane. In order to have a bond angle, I have to have a bond through the middle to another bond. There's no second bond in that plane. So there's no 120-degree angle either. 120-degree angle has been stolen by the addition of that extra lone pair. So the only angles that are here are these 90-degree angles and these 180-degree angles. 120 disappears because there's no other bond there. Now in Seesaw, it is there because we would still have, this bond set here. So that would be your 120-degree angle, obviously being squished a little bit by that lone pair pushed on it. All right, we're gonna call it right here. I'm not gonna have time to do the other 2. They are in the key, however, so I would encourage you to go look there for it. You should be able to find it. It'll drop here in exactly 4 minutes. So you should be able to see it there. And you can see I've gone through in this key, given some context there for most of these as well. So if you want to copy it down real quick, you can go there. We don't have time to go through everything piece by piece there. I want to thank you all for coming out though. I really appreciate it. Have a good night.